forces us to separate the subsets of Rn into two groups. One will be the measurable subsets of Rn and the other is the non-measurable subsets. The measurable subsets will follow our geometric intuition about length, area, volume, etc. And as well as that, it will also satisfy the finite additivity property, but this property will fail in the non-measurable subsets. Today we will see the notion of elementary sets and elementary measure of those sets. So we will define what are intervals and boxes in higher dimensions in n-dimensional Euclidean space, as well as what is an elementary set, and then we will define the elementary measure of those sets and prove that it does not depend on the choice of the description of your elementary set in terms of finite unions of disjoint boxes. So we can begin our study of measuring subsets of Rn from sets which have very simple structure, and these are called the elementary sets, and we will see that we can produce a method to give numerical value to each such elementary subset of Rn, which not only has the finite additivity property, but also it will conform to our geometric intuition via the notion of length, area and volume. So these are called elementary sets, and the numerical value that we will assign to elementary sets will be called the elementary measure. So let us begin in the first case. For the real line R, let's consider those subsets of R from which we can easily determine what should be the length of such a subset, and the easiest such subset that one can think of is in fact the interval from A to B, let's say. So of course we know that the length of the interval is B minus A. Now we can try to see if we have rather an open, the end at A, if it is open and the end at B is closed, then also the length will be, so let's suppose that this is a point X, then the length of this interval I, so let's call this I, length of this interval I will be B minus X, but here you have to take the limit as X approaches A from the right hand side. So again this will give you B minus A. Therefore we can consider all kinds of intervals which have either both endpoints closed, or one of them can be open, or even both of them can be open, and the length will still be the difference between the higher endpoint and the lower endpoint. So we make this definition for an interval. So if A is less than B, less than or equal to B, I will consider also the degenerate case when it is just 1 point, and in this case our length will just be 0. So I will consider A less than or equal to B, and these are all finite. Then an interval is a set of the form, so either you can have A, B both closed, A open, B closed, A closed, B open, and A, B both open. So any such set of R will be called an interval in our terminology, and we assign the numerical value let me denote it as M rather than L, so M for measure. M of such an interval AB is simply B minus A, and we can have all kinds of possibilities of A open, B open, both open, and so on. But in all such cases, we will assign the value B minus A to such an interval. So this is the same as A open, B closed. This is A closed, B open, and this is also equal to AB and open interval. So for all these cases, our numerical value is simply B minus A. In higher dimensions, in general, for Rn n greater than or equal to 1, we define a box as a Cartesian product I1 cross I2 cross In of intervals in R. So, for example, in dimension 2, if one of our intervals is AB and the other interval is CD, then our box will be simply the square with appropriate sides removed whenever we encounter an open endpoint. So in this case, our B endpoint is open, so this side will be open, and our D endpoint is open, so this side will also be open. So any such region enclosed by such lines will be called a box. So just from the general meaning of the term, we call it a box. Now for a box B, so this is a definition. For a box B in Rn, we define the numerical value m of B to be simply the product of all the intervals that B constitutes. So this is from 1 to n. So here, for this box B in the picture, we will have the measure of B to be simply B minus A times D minus C. So it's just the product formula for the area in this case. Similarly, in higher dimensions, this is the volume formula for a box. So now we have started with the most elementary notion of a subset, which has an obvious size, which is given by the length or the area or the volume. Now it is immediately clear, so let me write this as a lemma, that for x belong to Rn, if you take the set B plus x, which is x plus b, such that so this is in Rn, such that B belongs to B. So this is the translate of B by the vector x. Now this is again a box because at all the endpoints. For example, if you take B to B, in 2 dimensions, AB cross CD, then B plus X is simply A plus X, B plus X, Cartesian product C plus X, D plus X. And it's clear that the length of each of these intervals remains invariant because we are translating it in the x by an amount x. So this should be x1 and this should be x2 here. So x is x1, x2 vector in R2. So the first interval is translated by an amount x1 and the second interval is translated by an amount x2, but the resulting length remains the same. So m of b plus x is equal to m of b. This is an immediate lemma that we have. So now we can define what is an elementary set in Rn. So a set subset E of Rn is called elementary if it is a finite union of boxes. So for example, in dimension 2 we can have one box like this, another box like this, and our E can be the union of these two boxes. So this is an elementary set. So E, this is an elementary set for, in this case, in R2. So we can have any finite union of boxes and such sets will be called elementary sets. Now we have the following theorem. So let E be an elementary subset of Rn. Then first one is that E can be expressed as a finite union of disjoint boxes. Finite union of disjoint boxes. So our elementary subsets may have boxes which are overlapping, but the first part says that it can always be expressed as a finite union of disjoint boxes. Secondly, if E is a union of disjoint boxes Bi I equal to 1 to n, and E is also a union of another set of disjoint boxes Bi prime, so let me call it Bj prime, j from 1 to m. So in the first case we have n disjoint disjoint boxes, we have a finite union of n disjoint boxes, and in the second case we have a finite union of m disjoint boxes Bj prime. Then the sum over Mbi I from 1 to n is equal to the sum over j from 1 to m. Too many m, so let me write n prime here, n prime m of b j prime. So it doesn't matter what this part says, is that it doesn't matter what kind of partitioning of E you consider in terms of a finite union of disjoint boxes, so it is important to have disjoint boxes, then regardless of the partitioning, this sum of the measures of each boxes will be the same, and this common value will be denoted as M of E, and M of E is called the elementary measure of E. So let us prove the first part of the theorem. So we have to show that an elementary set E is a finite union of disjoint boxes. So let us begin with the simplest case when we have n equal to 1. So the dimension of Rn, here n is the dimension of the Euclidean space. So for n equal to 1 we have the real line R, and E is an elementary subset of R. So suppose, for example, that E can be written as a union of two boxes. So first one, let us say that it is a closed box, closed interval A1, B1, and the second one is A2, B2. So there is some overlap. Now we would like to partition this, so this is the union, so this whole region will be our set E. E is a union of the interval A1, B1, A1, B1 both closed, and the union A2, B2. So the obvious thing to do is to have the first interval should be this one, this is I1. The second interval should be this one, this is I2, and the third interval should be the rest, I3. So what we have done here is we have taken the endpoints of these intervals and we have arranged them in an increasing order from left to right. So A1, so here we have A1 less than or equal to A2 less than or equal to B1 less than or equal to B2. So you can even have the endpoints to coincide, so that's why I put a less than or equal to sign. Of course here in our example there is a strict inequality, but in general the endpoints can be the same. So so we have this we have arranged the endpoints of the intervals in increasing order, and then we can define our intervals I1 to be A1, A2. Here I am going to put an open end. I2 will be closed A2 open B1, and I3 will be closed B1 and closed B2. So at the endpoints here, at the least point and at the highest point, we have whatever, whether it is closed or open, we put that condition for the first one, and for the last one, whether it is closed or open, we also put the same. So now we can write our E as a disjoint union of I1, I2 and I3. So this simple geometrically obvious method works for more than one intervals, first of all, and So this was for our this was for a baby example which had A1 B1 union A2 B2. So then this is our decomposition where I1, I2 and I3 are given by this this expression. So now we can easily generalize to k intervals still in the dimension 1. So our E is equal to the union of ik, I equal to 1 to n, but now our ik's may not be disjoint. So this union may not be a disjoint union, but again we can arrange the endpoints of the intervals ik's. So we will have 2k endpoints. We have k intervals and each has 2 endpoints, so we have in total 2k endpoints in increasing order, and we can call it A1 less than equal to A2 less than equal to A3 less than equal to A2k. So we have 2k points which are now arranged in increasing order. So now we will do the same thing that we did in this example. So now define ik prime to be the closed ak and open ak plus 1 if k is from 2 to n minus 2. Okay, so here we are left with the least endpoint and the highest, most is the highest value endpoint. So here we have a1 and so this should be, yeah, so this is a n minus 1. When you have n minus 2 and you do a k plus 1, you end up with a n minus 1. And so this should be a2. So these the intervals with these endpoints are covered. What is left is a1 and an. So I defined I1 to be, I1 prime to be a1 a2 intersection with I1. Here I am taking the intersection because it may be open, I1 may be open at the point a1. So then you will end up with the open interval. The interval will be open at the point I1. And similarly, we define In prime to be a n minus 1 a n intersection In. So in this way we will have a collection of disjoint. So it's easy to check. So I leave it as an exercise that these ik primes, k from 1 to n, are disjoint intervals, and E can be written as the union of these disjoint intervals ik prime, k from 1 to n. So this proves our assertion in the case n equal to 1. This proves 1 for n equal to 1.